Welcome to the deep dive. We're the show that, cuts through the noise to get you the insights you actually need. Ever had that feeling with a Python script where it just feels sluggish? Or maybe a server that just locks up? Well, today we're tackling something you specifically asked us to look into. A really thorough exploration of Python threading and concurrent operations. Our mission today, basically to demystify these, let's be honest, sometimes complicated concepts. We want to equip you with the essential know-how for writing concurrent code that's clean, efficient, and importantly, responsive.
That's exactly it. This deep dive, it's structured right. We want to guide you starting from the real foundational ideas of concurrency and take you all the way up to some more advanced techniques. And the real goal here, it's not just about how to use tools like, say, thread pooling. It's really about getting when and why you should use threads in your actual day-to-day applications. Practical proficiency. That's the aim.
And yeah, to do that, we've got this great set of source materials. It really lays out the path nicely. It's structured to build your knowledge, step by step with plenty of practical examples, real world stuff that actually builds on itself, which I always find super helpful for making things stick. So let's just jump right in. Okay, first things first. Let's unpack this from the very beginning. When we talk about concurrent operations, these two terms pop up constantly. Concurrency and parallelism. What is the actual difference? Because they sound, well, pretty similar.
Yeah, they do. And it's a really crucial distinction, actually. A common point of confusion. Think of concurrency like this. You're dealing with many things at once, but maybe not literally at the same exact time. It means multiple tasks are making progress over some period, even if only one task is, like, actively running at any single microsecond. My go-to analogy, a juggler. They've got multiple balls up in the air, keeping them all moving, but they're only actually touching one ball at any given instant. All the balls are moving through their arc, they're making progress, but the juggler isn't handling them all simultaneously.
Ah, okay. So it's more about managing tasks cleverly, making it look like they're running together, even if the system's just rapidly switching focus, like maybe a really efficient single-lane road moving different cars through quickly, one after the other.
Precisely. That's a good way to put it. Now, parallelism, that's actually doing many things at once. Truly simultaneous execution. So if concurrency is our single juggler, parallelism is like having several jugglers side by side, each with their own set of balls, all working at the exact same moment. And for that, you need multiple processing units. Could be CPU cores, could be separate machines, whatever. The key is true, simultaneous execution.
Got it. That really does clear it up. But, Python often has its own way of doing things, right? Its own little quirks. Like this thing, the global interpreter lock, the GIL. What exactly is that? And why does it seem to come up all the time when people talk about Python concurrency?
That's the perfect next question, actually, because Python's approach to threading is pretty unique. And it fundamentally comes down to the GIL. At its heart, the GIL is what's called a mutex, a mutual exclusion lock. Its job is basically to protect access to Python objects, making sure that multiple native threads don't execute Python bytecodes at the exact same time within a single process. What this means is, even if you've got a fancy multi-core processor and you create multiple threads using Python's threading module, the GIL ensures that only one of those threads can be executing actual Python code at any one moment. Oh, hang on. That sounds like a huge limitation. If I'm trying to speed things up on my multi-core machine, why would I even use Python threads if this GIL thing just bottlenecks everything? Am I missing something here? It feels counterintuitive. You're hitting the nail on the head there. That's the core challenge and also the key insight about the GIL. For tasks that are CPU bound, things that spend most of their time doing calculations, not waiting around, the GIL does effectively prevent true parallelism in standard Python, like CPython. And that's why understanding it is so critical. It basically dictates when traditional threading is helpful and when it just won't give you the speed boost you might expect. But, and this is the really important nuance, the GIL is released during I/O operations, automatically.
Yeah.
So when your thread is just sitting there waiting for data from the network or reading from a disk or talking to a database, the GIL gets unlocked, you could say. And that allows other Python threads to run their Python code. This is the reason threading can still be incredibly useful for I/O-bound tasks. It's not about running calculations in parallel. It's about making your program feel responsive by overlapping all those waiting periods. It kind of shifts how you have to think about concurrency in Python.
Okay, that's a critical point. It totally reframes things. So if threads are actually great for I/O, how do we get started? Let's talk basics. The threading module.
Right, the threading module, that's your sort of entry point for creating and managing threads directly. Typically, you'll define a function or maybe a method in a class that holds the task you want the thread to run. Then you create a thread object, you pass your function to it, you kick it off with the start method. And if you need your main program to wait until that thread finishes, you use join. For instance, say you're simulating downloading a few small files from different places online. Each download could run in its own thread. While one thread is waiting for its file chunk to arrive over the slow network, another thread can start its download request. You're making good use of that waiting time. Basic threading like this works pretty well for, a handful of independent I/O tasks, where you just want to keep things moving along.
Okay, simple threads make sense for simple cases. But my brain immediately jumps to scale. What if I'm dealing with, hundreds of these tasks? Or thousands? Manually creating threads, destroying them, keeping track. That just sounds like a potential nightmare. Is there a more managed way, something cleaner, maybe like a thread pool?
You've just perfectly described what Concurrent.Future's ThreadPoolExecutor exists and why it's so useful. It's a much higher level way to handle threads, built right on top of the basic threading module. It simplifies things a lot. A thread pool is, well, it's pretty much what it sounds like. A collection of worker threads that are already created and just waiting for work. So instead of spinning up a brand new thread for every single little task to handle, you just submit your tasks to this pool, and an available thread from the pool grabs it and runs it. This approach is really beneficial. It manages resources much better. It cuts down massively on the overhead of creating and destroying threads constantly. And frankly, it just makes your code cleaner and easier to manage.
Right, so instead of me playing hiring manager for every tiny job, I just hand my stack of work to this ready-made crew and they sort it out. That sounds way more robust.
It really is. Think back to our file download example. Let's scale it up. Say now you're scraping hundreds of web pages, or you need to process thousands of log files concurrently. Instead of manually creating a thread for every single URL or file addop, you just submit each task, like scrape this URL or process this log file, to a ThreadPoolExecutor. The executor manages a pool of worker threads, maybe a fixed number, maybe it adjusts. It automatically hands out the tasks. It's just far more efficient and stable than juggling individual threads yourself, especially when the workload is large or unpredictable. It gives you a really structured way to run lots of I/O-bound stuff concurrently without all that manual fuss.
Okay, that makes total sense for those I/O tasks, waiting for networks, disks, whatever. But we just established that the GIL limits true parallelism for the CPU-heavy stuff. So this begs a really important question. When do you pick ThreadPoolExecutor versus its cousin, ProcessPoolExecutor? Is there a simple rule?
That distinction is absolutely vital, yeah. And it comes straight back to the GIL. ThreadPoolExecutor uses threads, right? And threads within a single process share the same memory space. Because of the GIL, like we discussed, this is perfect for I/O-bound tasks, tasks where threads spend most of their time waiting, network requests, file reads. While one thread is waiting, the GIL is released, another thread gets to run its Python code. Progress happens concurrently, even if not truly in parallel. You don't get true CPU parallelism, but you get great responsiveness for I/O. Now, ProcessPoolExecutor, that uses separate processes. Each process gets its own Python interpreter, its own memory space, and crucially, its own GIL. Because each process has its own GIL, ProcessPoolExecutor can achieve true parallelism for CPU-bound work. It can spread the load across multiple CPU cores effectively. So if you've got some heavy computation, maybe complex math, scientific simulations, big data number crunching, image processing, tasks where the CPU itself is the bottleneck, then ProcessPoolExecutor is usually the way to go. But if you're, say, fetching data from 1,000 websites, mostly waiting, ThreadPoolExecutor is your friend.
Got it. ThreadPoolExecutor for waiting, ProcessPoolExecutor for heavy thinking. Like two specialist teams. Okay, now, as we get into more complex stuff, managing shared resources between threads. That seems like where things could get messy fast. How do we stop threads from, tripping over each other? Things like race conditions or messing up shared data.
Yes. Welcome to the really interesting part of concurrent programming, and sometimes the most frustrating. When multiple threads try to access or change the same piece of data at the same time without any coordination. That's when you get problems. Race conditions are classic. The final result depends entirely on which thread gets there first, which can be totally unpredictable. Or you get data corruption, where the shared information just becomes inconsistent, nonsensical. I remember, spending a whole day hunting a bug once. Turned out it only happened when two threads tried to increase the same counter at almost the exact same microsecond. Some updates just got lost. Nightmare. To prevent this chaos, we use synchronization primitives. Think of them as traffic signals for threads. The most basic one is threading.lock. It's literally like having a single key. Only one thread can hold the lock at a T at a time. A thread needs to acquire the lock before it touches the shared resource and then release it when it's done. If another thread comes along and tries to acquire the lock while it's already held, it just has to wait, patiently. So for that shared error counter in our log parsing idea, you'd wrap the line counter plus equals 1 inside an acquire release block using a lock. Ensures only one thread updates it at once. Then there's threading and .event. This is more like a flag or maybe a traffic light. Threads can wait for an event to be set, like the light turning green. Another thread can set the event to signal something happened. This is super useful for coordinating groups of threads, like a main thread could set an event to tell all worker threads, okay, start processing now. And finally, threading semaphore. This one's like a bouncer at a club with a limited capacity. It allows a certain fixed number of threads to access a resource at the same time. Not just one, but maybe, say, 5. Imagine you have a service that can only handle 5 simultaneous file uploads. A semaphore initialized to 5 would ensure that only 5 upload threads can be active at any moment. Any others have to wait until someone leaves. These tools, locks, events, semaphores, they're your key strategies for keeping data safe and threads behaving nicely together.
That's a really helpful breakdown of managing access. But what about the data structures themselves? Are normal Python things like lists and dictionaries automatically safe from all this concurrent madness? Or do we need special versions?
Yeah, unfortunately, no. Your standard Python lists, dictionary sets, they are not inherently thread safe if multiple threads are trying to modify them concurrently. If you have multiple threads adding or removing items from the same list without any external locking, you can easily end up with corrupted data, missing items, or just plain weird behavior. This is where thread-safe alternatives are absolutely crucial. And the queue module is honestly a lifesaver here. Queue gives you a synchronized, ready-to-go thread-safe queue. It's specifically designed for passing data safely between threads. You can have producer threads adding items, like tasks or data, to the queue using put, and consumer threads can safely take items out using get. The beautiful part is, you don't need to mess around with locks yourself when using the queue. It handles all the necessary synchronization internally. Think about web scraping again. Producer threads find URLs and put them onto a queue. Queue, a pool of consumer threads, get URLs from that queue, scrape them, maybe put the results onto another queue. The queue acts as a safe buffer, making sure producers and consumers don't interfere with each other. Smooth, reliable data flow.
So it's like a built-in thread-aware conveyor belt for data, handling the coordination for you. That sounds like a massive help. Okay, so once we have tasks flowing nicely into a thread pool using safe queues, how do we manage the tasks themselves, like scheduling them, getting the results back, and crucially, what happens when a task fails? How do we handle errors gracefully?
Right, managing the life cycle. So in ThreadPoolExecutor, you typically schedule tasks using the submit method. You give it the function you want to run and any arguments. Now, submit doesn't just run the task immediately. It returns something called a feature object. This feature is really important. It's like a placeholder or a promise for the result of that task eventually. Or if the task crashes, it holds the exception. Later on, you can get the actual result by calling result on the future object. And here's the neat part about errors. If the task you submitted raised an exception, calling future.result will re-raise that same exception right there in your main thread. This means you can wrap your future.result, call in a standard try to accept, block, and handle errors just like you normally would. Now, if you've submitted a whole bunch of tasks, waiting for them one by one using result might not be ideal. That's where concurrent.futures.sCompleted comes in. It's fantastic. You give it your list of future objects and it yields them back to you as they finish, regardless of the order you submitted them. So if task number 5 finishes before task number 1, asCompleted gives you task 5's future first. Great for responsiveness, going back to scraping. Submit all your scrape tasks, get back a list of futures, then loop through asCompleted futures. As each future completes, you try calling result. If it worked, great, process the data. If it failed, like a network error on that specific URL, the exception gets raised, you catch it, log it, maybe mark that URL has failed, whatever. But it doesn't stop you from processing the results of the other successful scrapes. This makes error handling really robust. Your whole batch doesn't fail just because one task hit a snag.
We've talked quite a bit about I/O bound versus CPU bound and the GIL's impact, but real-world applications often mix these, don't they? Like maybe a web server that needs to fetch data from a database, I/O, and then do some complex calculation on it, CPU. How do you handle that mix effectively in Python, keeping the GIL in mind?
That's a super common scenario, absolutely. And the strategy here is usually about using the right tool for the right part of the job, combining threading and multiprocessing strategically. For the IO-bound parts, fetching from the database, receiving the web request, sending the response back threading with ThreadPoolExecutor is still usually your best bet. Why? Because even with the GIL, when a thread is blocked on I/O waiting for the database, waiting for the network, the GIL is released. This lets other threads run, handle other requests, keep the server responsive. You're efficiently overlapping those wait times. But then when you get to the part that requires heavy calculation, that CPU-bound work, That's where you typically hand that specific piece of work off to a process pool executor, or maybe even a dedicated background process using multiprocessing. By moving the CPU-intensive calculation to a separate process, you bypass the GI limitation for that specific task, allowing it to run truly in parallel on another core if available. So you orchestrate it. ThreadPoolExecutor manages the high volume of I/O-bound request handling, keeping things snappy.
And when a request needs heavy computation, it delegates just that computation part to a process pool executor to get the parallel speed up. It's like building a pipeline. Use threads for the waiting stages, use processes for the heavy lifting stages.
Okay, so it really comes down to analyzing your workload, breaking it down, and then picking the right concurrency tool for each specific piece. Smart. But even if we make all the right choices, how do we actually check if our concurrent code is performing well? And maybe more importantly, how do we debug those nightmare concurrent bugs, deadlocks or those race conditions that only seem to happen right before a demo?
Yeah, performance analysis and debugging. They definitely get trickier with concurrency, mostly because things aren't always deterministic. Execution order can vary. For performance, identifying bottlenecks is key. Is your code actually spending time waiting on I/O, like you expect? Or is it unexpectedly CPU bound? Or maybe are threads spending a lot of time just waiting to acquire locks? That's called lock contention. Profiling tools can help here. Even basic timing using Python's time module can give you clues. Understanding thread states is a thread running, waiting, locked is also important. For debugging, oh boy, deadlocks are a classic. Thread A holds lock 1 and waits for lock 2, while thread B holds lock 2 and waits for lock 1. Boom, stuck forever. Race conditions are sneakier, like we mentioned, because they depend on timing and might not happen every run. One common mistake is relying on print statements for debugging concurrent code. Sometimes the very act of printing can change the timing just enough to make the bug disappear. Maddening. Robust logging is usually a much better approach. Log key events include timestamps and definitely log the thread ID. This helps you reconstruct what actually happened in what order. For really tough cases, there are more advanced debugging tools and techniques, sometimes specific profilers designed for concurrency. But the core idea is always measure carefully. Try to isolate the issue and understand the potential interactions between your threads and shared resources.
Wow, okay. That was quite the journey. We went from the absolute basics all the way through to some pretty advanced strategies for handling complex concurrent stuff. So, reflecting on all this, what does it really mean for you listening in? We set out to give you a clear path, a structured way to get proficient with Python thread pooling and concurrency. And I really think we've unpacked a lot, hopefully demystifying these powerful but sometimes intimidating concepts.
I think so too. You should now have a much clearer picture of, concurrency versus parallelism, the whole deal with the GIL, when it matters, when it doesn't as much. And crucially, how to use the tools, basic threading, the very useful thread pool executor, and when to reach for process pool executor. More than just the tools, though. We talked about tackling the real challenges, synchronizing threads with locks and events, using queues for safe data sharing, managing tasks and handling errors properly within pools. The aim, really, was to empower you to write code that's not just concurrent, but also clean, efficient, and robust. Knowing when to apply which technique is key. And if you want to keep going deeper, absolutely check out the official Python docs. The pages for threading, concurrent.futures, and Q are excellent. Bookwise, Fluent Python by Luciano Romaglio has some fantastic, really insightful chapters on concurrency. Highly recommended. And while we focused on threads today, it's worth maybe looking into Asyncio later on. Python concurrency with Asyncio is a good resource there. It's a different approach, often complementary to threading. Look for online courses with hands-on labs, too. And honestly, browse GitHub. Find well-regarded open-source Python projects that use concurrency heavily. Seeing how others structure their concurrent code in real applications is invaluable. And maybe just a final thought to leave you with, something to ponder. As the software we build gets more and more complex, think about this. How might understanding these concurrency patterns, breaking problems down, managing simultaneous operations, how might that not just make your Python code faster, but actually change the fundamental way you approach designing solutions? In any language, it's more than just performance, it's a way of thinking about complexity itself, something to chew on.